while f is differential. As I told you, this is partial f partial x, that's partial f partial y. Now I will start, that's the gradient vector, that's the first component, partial f partial x, that's for the second component. I will substitute by the point which is 1 and 0, let's do 1 and 1. I will do exactly the same for normalizing my vector. Then I will multiply both of them together. That's the final step. It's 2 to 2. Same exact problem. This is the solution using the advantage of having a differential function. And the previous slide we saw we can use the main differential. Here is also, he wants you to determine the direction derivative of the function f at the point in the direction of the vector 2 and 1. Same steps, that's the domain. The function is differentiable through this domain. I got the unit vector normalized, so I'm dividing 2 and 1 on the magnitude of this vector. So it's a 2 to the power of 2, which is 4, 1 to the power of 2 is 1. The sum is equal to 5 under the square root. So it's going to be 2 over root 5, 1 over 2 root 5. Since the function is differentiable, it's a multiplication, as you can see, with exponential logarithmic. So it is defined differentiable along its domain. The second step is to get the gradient vector, already having the, having the unit vector, times the gradient vector at 0 and 1. So I will need to differentiate this function, first with respect to x, then substituting, then differentiating with respect to y, then substituting by the point at 0 and 1, as you can see. So this guy is negative 2, that guy is positive 3, multiplied by these results. So this is the final answer for this problem. That's the directional derivative of this function in the direction of 2 and 1, as you can see. That's another problem. He wants you to get the directional derivative of the function at the origin in the direction of the vector 1, 1. And once more, I will test with you that the unit vector 1, 1, it is normalized in this case. Now I will need to find or to use the law of the definition, because this function, it is a piecewise function. So I will use the substitution at the origin, t1 over root 2, t1 over 2. I will take these results and start substituting in my function. So replacing the x by t over root 2 and y by 2 over root 2, exactly like this. I can take some, I can simplify it. So I think we can take those parts together and they make this part together. So I will take, first of all, I will try to reorganize it. It's gonna be 2 with 2, so it's gonna be t cubed over root 2. This is gonna be sine divided by t squared, and t squared will be multiplied by t, so it's gonna come up to t cubed. So after simplification, this is the case. If I want to take the limit, this part is gonna equal to, if you eliminate the values of t, so I'm separating them to two limits, which is gonna be 1 over root 2. And for this part, 1 over 2 root 2 is gonna be outside. Taking the limit of sine, the angle divided by the angle, both the angles are equal to each other. So the limit here is equal to 1. And so the result for this special limit is gonna be 1 over root 2 plus 1 over 2 root 2, as you can see. And now I have the value of my function already exists, as you can see, which is 3 root 2 over 4. Perfect evaluation for the directional derivative in this direction. I believe I added plenty of problems on the directional derivative. But before going further in more exercises and problems, I want you to remark that according to theorem 3.7, if f from Rn into R is a differentiable function at A, then the gradient, and if the gradient vector is equal to 0, then all directional derivatives on A at A are null vectors. If I want to get the maximum directional derivative and the gradient vector of f at A is not equal to 0, then the maximum value of the directional derivative of f at A is obtained along the direction of the gradient vector gradient f of a. And this maximum value with the gradient vector, as you can see, it will be in the direction of the gradient vector. So the maximum directional derivative at certain point, it will happen in the direction of the gradient vector. And the minimum also at this point, it will be negative in the direction of the negative value of the gradient vector as we use it. Another important property of the gradient vector at a certain point, that it is perpendicular to the level curve. This is why we usually, once we get the gradient vector and we substitute by a point, it will give us the normal vector at this point, and so we can find the tangent plane or the normal straight line as various applications in engineering as will arise or can be benefited from this part. And we will go through it in the next slides, inshallah. So if this is the level curve that we are talking about, and this is AB, this is going to be the direction of the gradient vector at this point for this level curve. That's another problem with the same steps. You want you to evaluate to find the directional derivative of this function at 1 and 1 along the unit vector, which is 1 over root 2, 2 over root 2. I believe that's a unit vector. So it's a direct application, of course. That's the gradient vector of the function at 1 and 1. I will multiply it by the unit vector. The gradient vector, it means I will differentiate with respect to x, differentiate with respect to y, then substitute by 1 and 1. Already have them, which is really very simple. That's the first derivative with respect to x for this function. And now I will substitute by 1 and 1. That's the first derivative with respect for f with respect to y at 1 and 1, which is going to be negative 1. That's the gradient vector, okay, at 1 and 1, which is going to be 4 and negative 1. Multiplying them together will lead to the fact that I will have 4 over root 5 minus 2 over root 5. That's the value of our directional derivative for this function at the indicated point and add the vector as I told you. Okay, I will stop today at this part. Tomorrow I will start from here. I have a couple of problems on the directional derivatives, and I will go through them tomorrow in order to have you all here with me. So thank you very much for attending today. It's my pleasure. Please go through them, through this lecture, and try to solve, as I told you plenty of times, try to solve as much as possible from all of these problems. Thank you very much, and I will see you tomorrow, inshallah. Thank you. Bye-bye.